Hello there, and welcome to Sleepy Astra. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. All you need to do now is rest and let your mind relax. Because tonight we'll float through about 100 gentle facts about a rare visitor from another star system, 3I Atlas, only the third of its kind ever seen. We'll explore its discovery, its path, its chemistry, and calm comparisons you can picture. And just before we begin, if these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others discover these calm journeys too. Now let's begin. It started on a quiet night, July 1st, 2025. In Chile's Atacama Desert, one of the NASA-funded Atlas telescopes was doing what it does every clear evening, sweeping huge patches of sky with a wide-field camera, looking for anything that moves. Most nights the software flags familiar stuff, routine asteroids, known comets, even passing satellites. But on this night, it caught a faint, slow-drifting point that didn't match any predicted path. Atlas exists for exactly this kind of moment. The system, short for Asteroid Terrestrial Impact Last Alert System, was built to find potentially hazardous objects by scanning and rescanning the sky, then comparing images to spot motion. When something new appears, the data goes to the Minor Planet Center for confirmation. For the faint dot found in Chile, follow-up came quickly. Its motion didn't look like a sunbound object at all. It followed a hyperbolic path, an open curve that swings past the sun once and keeps going. In simple terms, a one-way visit. By July 2nd, the Minor Planet Center confirmed what the orbit implied. This was the third interstellar object ever seen passing through our solar system. It was named 3I Atlas, 3I for Third Interstellar, and Atlas for the survey that spotted it. As observations accumulated, the object also received its comet designation C2025N1 Atlas, reflecting clear signs of cometary activity. If you retrace our view a little earlier, the comet had been hiding in plain sight for weeks. Once astronomers knew where to look, they found pre-discovery images in survey archives, extending back to mid-June 2025. That's common with faint, fast movers. The evidence is there, but it only pops out after the fact, when the path is known well enough to search for it. Here's the simple picture so far. A faint traveler appears in Chilean images on July 1st. Follow-ups confirm a hyperbolic path. The Minor Planet Center declares it interstellar the next day. And the community settles on the working name 3I Atlas with the formal comet tag C2025N1 Atlas. Each step is careful, routine, and quietly exciting, because interstellar objects are rare. Before this, we had only Oumuamua, 2017, and 2I Borisov, 2019. Now there was a third. One more detail that helps the story click into place. Distance. At discovery, 3I Atlas was within the orbit of Jupiter, hundreds of millions of miles from the Sun. Far, but close enough for big surveys to catch it, and for follow-up telescopes to start planning. You don't need to memorize the number, just picture this. It's moving fast enough that the Sun's gravity couldn't capture it into orbit. So if you're listening in the dark, think of it this way. A quiet system designed to guard our planet saw something unusual. The orbit said, "Visitor." The naming followed the rules. And suddenly, we had a new chapter in a very short book. Our third known object from another star system, passing through our neighborhood on a single graceful arc. Once the Minor Planet Center flagged the orbit as hyperbolic, telescopes across the world turned toward this faint newcomer. On the night of July 2, 2025, observatories in Hawaii and Chile gathered fresh images. Each facility added points of light to the growing data set, feeding into international databases. In less than 24 hours, dozens of positions traced a curve through the stars, an unmistakable arc that marked the path of something just passing through. Amateurs joined in too. With small telescopes and long exposures, they began to see what larger instruments hinted at: a coma, a fuzzy glow surrounding the nucleus. It was faint at first, little more than a smudge, but by July 2nd, it was clear enough that professional reports described the object as cometary. That's what earned it the full comet designation, C 2025 N1, Atlas, in official bulletins. To astronomers, that label meant two things. First, activity was being observed, and second, we had an interstellar comet, not just a bare rock. Every new observation from professional and amateur telescopes alike arrived there, checked, and logged. Within a day of discovery, hundreds of data points had already narrowed the orbit. The numbers made one conclusion inescapable. The eccentricity of the orbit, the measure of how open it is, was greater than 1. That value is the dividing line. Less than 1, you're bound to the sun. Greater than 1, you're on a one-way trip. 3I Atlas's eccentricity was well above 1. There was a sense of quiet wonder in the way astronomers spoke about it. In 2017, Oumuamua had come and gone so fast that most large telescopes barely had time to react. In 2019, Borisov had been brighter, but it still hurried past. This time, the third visitor arrived with a touch more patience. Early estimates suggested it would remain observable for months, giving scientists a better chance to study it in detail. Observatories with specialized instruments prepared quickly. Facilities with spectrographs, tools that split light into its rainbow of colors, pointed at 3I Atlas to search for chemical signatures. The first hints suggested carbon-bearing molecules were present, though the data was faint and needed confirmation. The important part was simple. The comet was active, it was shedding material, and we had time to watch. Picture this scene. Late at night, astronomers on mountaintops in Hawaii and Chile check their monitors. On the screen is a small blur against a field of pinpoint stars. It doesn't look dramatic. To the naked eye, it would appear like nothing at all. But to those who know what they're seeing, it is history in motion. An object from another star system, warming in the sun's light, releasing ancient ice that condensed around some other star long before ours ever noticed. By July's first week, 3I Atlas was no longer just a faint dot with an odd orbit. It had become a confirmed interstellar comet, tracked by a global network of professionals and amateurs, each data point weaving into a story that was only beginning to unfold. By mid-July, attention turned to space telescopes. Ground-based instruments had done their part, confirming activity and measuring the orbit. But faint objects in crowded star fields are always tricky to study from Earth. That's when the Hubble Space Telescope came into play. Its sharp vision offered something no ground telescope could match: the ability to resolve the faint glow of the comet against the starry backdrop with crisp clarity. Hubble's first images showed what astronomers had suspected: a delicate bluish tail extending thousands of kilometers behind the nucleus. It wasn't long or bright by the standards of great comets in history. It would never rival Hale-Bopp or Neowise in the naked eye sky. But for scientists, that tail mattered. It confirmed that 3I Atlas wasn't just a rock slipping past. It was active, venting gas and dust, behaving like a comet should. Spectrographs attached to telescopes on Earth supported the picture. They picked up faint emissions from carbon compounds, the telltale gases that stream away when sunlight warms an icy surface. These early chemical clues suggested that 3I Atlas carried the same kinds of materials we find in ordinary comets from our own solar system. And yet, the fact that it came from another star system made those same gases suddenly extraordinary. These were ices that had formed light years away, shaped under the chemistry of a different star, and now they were drifting off into space right in front of us. Astronomers spoke cautiously, as they always do with something new. At conferences and in email threads, they began asking, "Is this comet more like Borisov, icy and bright, or does it hide puzzles like Oumuamua?" Oumuamua had been long and thin, with no gas at all, while Borisov had been classic in shape and behavior. 3I Atlas seemed somewhere in between, clearly active but not dramatic, cometary but modest. The excitement was balanced with care. Estimates of its nucleus size varied, with some suggesting a few kilometers across, others a little smaller, but all hedged with uncertainty. Reflectivity was debated too, how bright the surface really was. Even its rotation rate was unclear, inferred only from tiny variations in brightness. Each measurement came with a margin of error, but together they began to sketch an outline of this interstellar traveler. What's striking is how calm the process felt. The press releases were factual, the tone measured. There was no need for exaggeration. This was already a rare gift, only the third interstellar object in history, and the first we could observe with such a clear cometary identity. The mood among scientists was one of quiet appreciation. They knew how fleeting these opportunities are, here for a short while, then gone forever. For backyard observers, the experience was humbler, but no less meaningful. Through small telescopes under suburban skies, 3I Atlas looked like a faint, fuzzy star, not impressive, not bright, but deeply significant. The knowledge of what it was transformed the view. Imagine adjusting a telescope, centering a dim blur, and remembering that this blur had traveled light years to arrive here, carrying the signature of another star system in its dust. So, by the middle of July, the story had shifted. What began as a faint, suspicious point in Chile was now confirmed as a living comet, trailing a tail seen by Hubble, releasing gases seen by spectrographs, and studied by a worldwide network. Scientists compared, measured, and speculated, always with humility. For the rest of us, it was enough to know a messenger from beyond the sun was with us, passing quietly through our skies. By the end of July, the discovery phase of 3I Atlas had become a shared project in the truest sense. Professional observatories tracked its path with precision, but amateurs played a vital role as well. From backyards and small domes, they gathered images, checked positions, and added their contributions to the same databases the largest observatories used. That blend of efforts, giant telescopes on mountaintops and hobbyist gear under city skies, created a picture far richer than either group could build alone. The Minor Planet Center acted as the beating heart of this network. Each new measurement, whether from a billion-dollar facility or a personal setup, was logged, verified, and added to the orbit. Updates flowed daily, each one tightening the curve of 3I Atlas's trajectory, showing exactly how it threaded its way past the sun. The orbit grew more certain, the speed more exact, the predictions more solid. The comet's eccentricity was no longer just above 1, it was firmly interstellar, its path confirmed beyond doubt. For scientists, those early weeks were precious. Oumuamua had slipped away almost before they could react. Borisov had passed quickly too, bright but brief. 3I Atlas, though, seemed to linger just long enough to allow a fuller study. Researchers scheduled larger telescopes, not in a rush, but in steady anticipation. There was time now to prepare, to refine observing campaigns, to ask smarter questions. The tone of those weeks was one of measured excitement. Instead of wild headlines, the news felt almost gentle. Another interstellar visitor, our third. Articles explained what hyperbolic means, why 3I was special, and how rare such events are. For the general public, it was a curiosity. For astronomers, it was history. And maybe that balance is what made 3I Atlas feel different. It wasn't a spectacle blazing in the sky, nor a puzzle vanishing before we could solve it. It was something quieter, a visitor we could actually watch, slowly, carefully, with patience. Think of those July nights. Across the globe, telescopes, both mighty and modest, turned toward the same faint smudge of light. In Hawaii, a giant mirror on a mountaintop. In Europe, a small amateur scope pointed from a backyard. In Chile, the Atlas survey that first spotted it. All of them watching the same thing, sharing the same data, writing the same story together. By the time July drew to a close, 3I Atlas was no longer a stranger. Its orbit was pinned down, its cometary nature confirmed, its place in history secured as the third interstellar object ever observed. What began as a faint dot in the desert sky had become a global collaboration, a reminder of how science often works best, with many eyes, many hands, and a quiet sense of wonder. And so the discovery phase ended. The comet was real, interstellar, active, and tracked. The next chapters would move beyond the moment of finding, into deeper questions of what it was made of, how big it might be, and what stories it carried from its home among the stars. With the discovery phase complete, astronomers turned their attention to the comet's physical nature. What exactly was this interstellar visitor like? How big was it? How bright? And what did that tell us about its journey? The first estimates came from brightness. Astronomers measure an object's apparent magnitude, the way its light looks to us from Earth, and then calculate what that would mean if the object were placed at a standard distance from both the Sun and Earth. That value is called the absolute magnitude, and it gives a rough sense of the nucleus size. For 3I Atlas, the numbers pointed towards something on the order of a few kilometers across, probably between 3 and 5 kilometers in diameter. That's in the same ballpark as many solar system comets. To make that easier to picture, 3 kilometers is about the length of 35 football fields end to end. Imagine that much ice and dust, packed into a single body, drifting between the stars for millions of years before swinging into our neighborhood. Brightness also hinted at its reflectivity, or albedo. Comets are usually dark, covered with carbon-rich compounds that absorb sunlight. Early analysis suggested 3I Atlas was no exception. Its surface reflected only a small fraction of the light that struck it, making it look blacker than asphalt. That fits the pattern of other comets, which are often described as dirty snowballs. But in this case, the snowball came from another star system. Another clue came from how its brightness changed over time. As 3I Atlas approached the Sun, it brightened steadily, though never dramatically. it didn't become a naked-eye spectacle. Instead, the curve suggested gentle but consistent activity, gas and dust lifting off the surface at a modest rate. In other words, it was alive, but shy. For astronomers, that was actually a gift. A comet that grows too bright too quickly can be unpredictable, fragmenting or fading. 3I Atlas's steady rise made it easier to model. Each increase in brightness gave a data point for understanding how fast the comet was shedding material. And each data point added a brushstroke to the picture of its nucleus. Size, brightness, albedo. Taken together, the portrait was of a typical comet nucleus, just a few kilometers wide, dark, and quietly active. And yet the context made it extraordinary. This wasn't material left over from the formation of our solar system. This was material forged around another star, perhaps billions of years ago, now carried across interstellar space to be glimpsed for the first and only time. So the first answers about 3I Atlas's characteristics were simple, almost ordinary. Small, dark, active. But the fact that it came from beyond the sun gave those ordinary qualities a sense of wonder. If the size of 3I Atlas was modest, its speed was anything but. From the very first calculations, it was clear that this object was moving far faster than anything tied to the sun. That number is hard to picture, so let's slow it down with comparisons. Commercial jetliners cruise at around 0.25 kilometers per second, meaning the comet is moving about 250 times faster than a passenger plane. Even the International Space Station, orbiting at a brisk 7.7 kilometers per second, looks slow beside it. 3I Atlas is roughly 8 times faster than the ISS. It also outpaces any spacecraft we've ever launched. The Parker Solar Probe, humanity's fastest creation, set records approaching 190 kilometers per second during close passes by the sun, but only with the help of repeated gravitational assists. For 3I Atlas, this speed is simply natural. It arrived with it, a gift of the gravitational slingshots of its home star system long ago. That speed is also the key to why it cannot be captured. In orbital mechanics, this is described by its eccentricity, a measure of how open the path is. Bound orbits like Earth's have eccentricities less than 1. Hyperbolic paths like this one are greater than 1. 3I Atlas's eccentricity is comfortably above that line, which is why we know it's not from here. Another way to think of it, imagine dropping a stone into a pond. Most ripples circle back and forth in closed loops, but every so often, a disturbance sends a ripple shooting outward, never to return. 3I Atlas is that outward ripple in the solar system, moving too fast for gravity to pull back. This speed isn't just a number, it's also a clue to its past. Objects don't usually drift at such high velocities on their own. They are often ejected by gravitational interactions, perhaps with a giant planet in another star system, or with a cluster of siblings early in its history. Long ago, something in its home neighborhood gave it a push, strong enough to fling it into the galactic sea. That's the momentum it carried with it across light years, momentum we now measure as a few dozen kilometers per second. For us, the number means time is short. A comet moving this quickly will only be within reach for a matter of months. Already, astronomers know that by the end of 2025, it will be too faint to study in detail. Every night of data counts, because each night it is pulling farther away. We're describing a traveler who can lap the Earth in minutes, who outruns spacecraft with ease, and who has momentum tied to a star we'll never see. That speed defines the comet as surely as its size or brightness. It is what makes 3I Atlas a visitor, not a resident. Once astronomers had a handle on 3I Atlas's orbit, size, and speed, the natural next question was, what is it made of? That's not a simple thing to answer for a faint, distant comet. But light carries clues, and scientists used every photon they could gather to piece together the picture. Telescopes equipped with spectrographs split the comet's faint glow into its component colors, searching for the chemical fingerprints of escaping gases. Early results revealed emissions consistent with carbon-bearing molecules, compounds like CN, cyanogen, and C2, diatomic carbon. These same signatures are common in the solar system comets. They are what give cometary comas their greenish tints when bright enough. And they signal that 3I Atlas carries similar volatile ices to those found in our local neighborhood. That was remarkable in itself. It meant that despite forming around another star, perhaps billions of years ago, the comet's chemistry wasn't alien in the extreme. The building blocks, water ice, carbon-rich compounds, dusty silicates, seemed familiar. In other words, the processes that formed comets in our solar system may also operate elsewhere in the galaxy. But there were also differences. The coma of 3I Atlas was faint, much more subdued than a typical bright comet passing near the sun. That suggested that while it carried volatiles, it wasn't shedding them in great amounts. Some scientists speculated that long exposure to interstellar radiation had altered its surface, building up a dark crust that limited outgassing. Others suggested the nucleus might simply be smaller than average, offering less material to sublimate. Dust was another piece of the puzzle. Images showed that the tail was delicate with fine particles scattering light in the blue range. That hinted at a relatively fresh release of dust grains, tiny and light enough to be carried by solar radiation pressure. The presence of dust alongside gas confirmed that this was no inert rock. It was active, alive in the cometary sense, even if modestly. For context, think of the comets we know well, Halley's Comet, for instance. When Halley nears the sun, it erupts with jets of gas and dust, bright enough to be seen without telescopes. 3I Atlas, by comparison, was far more subtle. You would never see it with your naked eye, and even in telescopes, it was just a faint blur. But at the scientific level, even a faint coma is enough to speak volumes. There's also something quietly profound in knowing what those molecules represent. The CN bands, the carbon emissions, they formed around another star, condensed in a protoplanetary disk we'll never see. They sat frozen for eons in deep space, untouched, until this comet strayed near our sun and released them. The atoms in its glow carry the chemical story of another world. And so, when scientists describe 3I Atlas's composition as ordinary, they don't mean dull. They mean familiar. This interstellar traveler appears to be built from the same ingredients that shape our comets: water ice, carbon, dust. But that ordinariness is what makes it extraordinary. It suggests the recipes of planets and comets are not unique to us, but shared across the galaxy. When you look at a comet through a telescope, it's easy to imagine it as a bright, icy snowball. The truth is the opposite. Most comet nuclei are dark, very dark, covered in carbon-rich material that absorbs light rather than reflects it. Astronomers call this property albedo, and 3I Atlas seems to fit the pattern. Early brightness models suggested that its albedo was extremely low, on the order of a few percent. To picture that, fresh snow reflects about 80 to 90% of incoming sunlight. Asphalt reflects about 10%. Coal-like surface reflects around 4%. 3I Atlas likely sits in that same coal-like surface range, blacker than asphalt, nearly as dark as the blackest soils. To a passing photon of sunlight, the comet is less a mirror and more a sponge. Why so dark? Comets begin as mixtures of ice and dust, but repeated exposure to solar heating, or in the case of interstellar objects, cosmic rays and ultraviolet radiation during their long voyages, changes their surfaces. The lighter ices sublimate away, leaving behind a crust enriched in heavier, carbon-based compounds. This crust can build up for millions of years, turning the outer shell into a hardened, darkened rind. When the comet nears a star again, gas and dust escape through cracks, but the surface itself stays blackened. For 3I Atlas, the journey was far longer than most. Between star systems, there is no warming sunlight, only the steady drizzle of cosmic radiation. Over tens of millions of years, those invisible particles could have slowly transformed its skin. Scientists suspect that's part of why its activity seemed modest. A dark, crusty surface insulating the ices within, forcing the gas to escape more gently. Color measurements added to the picture. Broadband filters suggested that 3I Atlas reflected light with a slightly reddish tint, not unlike many Kuiper Belt objects in our solar system. That's a sign of complex organic compounds, so-called tholins, on the surface. These substances form when radiation alters simple molecules like methane or ethane, creating reddish-brown residues. They don't tell us much about habitability or life, but they do reveal a chemistry rich in carbon, capable of building complexity. To put it simply, if you could hold a chunk of 3I Atlas in your hand, ignoring for the moment the vacuum and the freezing cold, it would look less like a snowball and more like a lump of black ice mixed with tar and dust. It would be fragile, porous, and very, very dark. Only when warmed would it reveal the hidden ices within, hissing softly into vapor under sunlight. This darkness is part of what makes comets so subtle in the sky. Even with a tail, 3I Atlas never came close to being visible to the naked eye. It remained a challenge for backyard telescopes, and even professionals described it as faint. Yet the same property that made it hard to see also made it interesting. Its blackened shell was a physical record of its time in interstellar space, a surface sculpted not by our sun, but by the galaxy itself. So while its nucleus may be small, its color and surface tell a longer story, one of endurance. A body formed in another star's nursery, ejected and darkened during a long interstellar crossing, arriving here not gleaming and fresh, but worn and shadowed, carrying scars from the vastness between the stars. Comets don't just travel, they also spin. And for 3I Atlas, understanding its rotation became another piece of the puzzle. The comet is far too small and faint to see as anything but a point of light in a telescope, but even points of light can carry hidden clues. Astronomers tracked its light curve, the subtle rise and fall of brightness over time. If the nucleus is irregularly shaped, or if active areas on its surface rotate into and out of view, the amount of sunlight it reflects will fluctuate. By measuring these variations, scientists can estimate how quickly the body spins. For 3I Atlas, early light curves showed gentle periodic changes. The variations were not sharp, which suggested a relatively slow rotation, likely on the order of several hours to perhaps half a day. That's slower than many small asteroids, which can spin every couple of hours, but consistent with comets, which are often less dense and more fragile. The shape was harder to pin down. but the data hinted at an irregular form. Most comets aren't neat spheres. They're lumpy, fractured, more like potatoes or dumbbells than marbles. Oumuamua had been elongated like a cigar or maybe a pancake, while Borisov had seemed more typical. 3I Atlas's brightness changes were modest, suggesting it wasn't as extreme in shape as Oumuamua. But it wasn't perfectly round either. Somewhere in between, an uneven chunk of ice and dust, with ridges and hollows left by billions of years of cosmic weathering. Rotation matters for another reason. It affects how gas escapes. If a comet spins rapidly, jets of gas can erupt in bursts, shifting its motion slightly. In the case of 3I Atlas, the gentle brightness variations suggested a stable, moderate spin, unlikely to fling material violently. That fit with its overall character: modest activity, a faint tail, steady rather than dramatic. But even modest spins can shape a comet's future. Over time, the gentle torque from outgassing, called the Yorp effect when applied to asteroids, can alter a body's rotation. A comet can gradually spin up or slow down, and in rare cases, even break apart if the stress becomes too high. With 3I Atlas, the risk seemed low. Its activity was mild, its spin moderate, and its time in the solar system brief. It would slip through without major change. Still, the thought lingers. What would it be like to stand on such a surface? On a body just a few kilometers wide, gravity would be so weak that you could leap into space with a strong jump. The horizon would curve tightly. And as the comet rotated, the sun would rise and set quickly, casting long shadows over a landscape of dark ice and dusty slopes. That scene is imagined, of course. We will never visit 3I Atlas. But the physics give us a glimpse. So the portrait of rotation and shape adds another layer. This interstellar comet is not a smooth, round pebble, but an uneven, slowly turning fragment, spinning steadily as it glides through our solar system. Its lumpy silhouette and quiet rotation are not dramatic, but they are exactly what you'd expect of a survivor, a small body that has drifted for millions of years across the galaxy, still intact, still turning, still carrying its story onward. Size, brightness, speed, and spin tell us part of the story. But to imagine 3I Atlas as a real object, we also want to know its mass and density. In other words, how much material it holds and how tightly that material is packed. For comets, those are always tricky questions because we can't simply weigh them on a scale. Instead, scientists combine indirect clues to estimate. For 3I Atlas, the best starting point was its size, likely between 3 and 5 kilometers across. If it were made of solid rock, that would imply a huge mass, tens of trillions of tons. But comets aren't solid rocks. They are fragile mixtures of ice and dust, more void than substance. Measurements of comets in our solar system, like Halley or 67P Churyumov-Gerasimenko, the comet visited by ESA's Rosetta spacecraft, show densities of only about 0.5 grams per cubic centimeter, less than half the density of water. In simple terms, they are lighter than ice cubes. If 3I Atlas shares that same porous nature, then its total mass might be on the order of tens of billions of tons, not trillions. That's still enormous, comparable to the mass of a large mountain, but much less than a rocky asteroid of the same size. Think of a loosely packed snowbank rather than a granite boulder. Why so porous? Comets form in the cold outer reaches of star systems, where ices condense and dust clumps together slowly. They never experience the pressure and heating that hardens planets. Instead, they remain fragile, with voids and cavities running through their interiors. You could imagine 3I Atlas as more foam than stone, a structure of icy grains, lightly held together by gravity. This porosity explains why comets can behave so dramatically near stars. As sunlight warms them, trapped gases escape through cracks, carrying dust with them. Sometimes the pressure is enough to split a nucleus apart, as happened with comet Shoemaker-Levy 9 before it collided with Jupiter in 1994. For 3I Atlas, activity was modest, but the same principle applies. Sunlight loosens gas from within, and the comet exhales into space. From Earth, we'll never pin down its mass precisely, but rough estimates suggest something in the range of 10 billion to 100 billion tons, a staggering weight, even for such a fragile body. Yet in cosmic terms, it's small, a speck drifting between stars, one of who knows how many billions. Imagine standing near such a nucleus. If it were possible, you could dig into the surface with your hand and find it crumbly, fragile, like compressed snow. A heavy stone dropped from a meter up might not even shatter. It would simply sink into the dust and ice. Gravity would be so weak that a running jump could launch you into the sky. And beneath your feet, cavities of empty space might lie hidden, formed by ancient gas pockets long sealed by frozen crust. So while the numbers for mass and density may sound abstract, they paint a vivid picture. 3I Atlas is a lightweight wanderer, more fragile than any mountain, more porous than pumice, held together by little more than frozen ices and the faint pull of its own gravity. That fragility is part of why interstellar comets are so special. They are not sturdy rocks hardened by time, but delicate messengers carrying unaltered material from the birthplaces of stars. If you want to imagine the true nature of an interstellar comet, you have to think about temperature. For most of its life, 3I Atlas has traveled far from any star, in the deep cold of interstellar space. Out there with no nearby sunlight, the background temperature is just a few degrees above absolute zero, about minus 270 degrees Celsius. That's minus 454 degrees Fahrenheit. That is colder than any place on Earth, colder than liquid nitrogen, colder than almost anything we can create in a laboratory. In those conditions, the comet's ices were locked solid. Water, carbon dioxide, carbon monoxide, all frozen harder than rock. For millions, maybe billions of years, 3I Atlas drifted in that frozen state, untouched, insulated by the vacuum of space. Its surface was battered only by cosmic rays which slowly darkened it, but nothing ever warmed it. That began to change when it entered the solar system. As it drew closer to the Sun in mid-2025, even at distances beyond Mars, sunlight began to stir the outer layers. Comets are sensitive. A little heat goes a long way. At temperatures of minus 150 degrees Celsius, that's minus 238 degrees Fahrenheit, some carbon-based ices already start to sublimate, turning directly into gas. By the time 3I Atlas approached the inner solar system, the surface layers had warmed enough to release a thin halo of gas and dust, the faint coma seen in July. Compared to brighter comets, though, 3I Atlas remained modest. Its coma was small, its tail delicate. That suggested its surface had a thick, insulating crust, material-baked and darkened by eons of cosmic exposure, holding the deeper ices in place. Only when sunlight cracked through did gases escape, carrying fine dust with them. Scientists modeled how the heat wave would move into the nucleus. Just a few centimeters below the surface, the temperature stayed much colder. Deeper still, perhaps only a few meters down, the ices were likely untouched, preserved in interstellar stasis. If you could somehow drill into the core, you'd find pristine ices nearly as cold as when the comet first formed. It's a strange duality. The surface blackened and warmed, exhaling softly into space, while the interior remained frozen and ancient. That makes comets like 3I Atlas time capsules. The outer crust shows the scars of interstellar travel. The inner core preserves the chemistry of a star system we can never visit. Temperatures also explain its behavior near the sun. Unlike some comets that erupt with sudden jets, or even fragment under thermal stress, 3I Atlas stayed calm. Its crust likely prevented dramatic breakups, allowing only a gentle, steady release of gas. That steadiness gave astronomers confidence it would survive its passage around the sun without major disruption, offering a longer window for study. For us, the numbers may sound abstract, but picture it like this: a body colder than any ice on Earth, ink-black shell-like surface on the outside, faintly glowing with released gas when warmed just enough by our sun. The heat of a summer's day here on Earth is more than 300 degrees warmer than its surface ever was in interstellar space. And yet, for 3I Atlas, the faint touch of sunlight is enough to awaken it. So temperature is more than a statistic. It's the rhythm of the comet's life. Frozen silence for ages, a brief stirring near a star, then back into the cold again. 3I Atlas has followed that rhythm for longer than we can imagine, and in 2025 we were lucky enough to witness one of its rare, warm awakenings. After weeks of observation, one of the clearest questions astronomers asked was, how does 3I Atlas compare to the comets we already know? In many ways, that's the easiest way to understand it, by holding it side by side with familiar neighbors from our own solar system. On the surface, 3I Atlas looks surprisingly ordinary. Its size, just a few kilometers across, puts it right in the middle of the range for cometary nuclei. Comet 67P Churyumov-Gerasimenko, the one visited by the Rosetta spacecraft, is about 4 kilometers across. Halley's Comet is closer to 11. Against that backdrop, 3I Atlas doesn't stand out as unusually big or unusually small. It's typical. Spectra show carbon-bearing molecules, dust, and water ice, just like in comets born here. If you looked only at its chemistry, you might assume it came from our own Oort cloud. That ordinariness is fascinating because it suggests the recipe for comets isn't unique. Across light years and star systems, the same ingredients seem to assemble in the same way: frozen water, carbon compounds, silicate dust, all mixed into fragile dark bodies. But look closer, and the differences emerge. For one, its activity was faint. Comets that dive into the inner solar system often erupt with jets, growing bright tails that can span millions of kilometers. 3I Atlas had a coma and a tail, but they were modest, subtle, requiring careful telescopes to see. That restraint may come from its darkened surface, hardened by eons of interstellar exposure. Most local comets spend their lives orbiting the sun every few centuries, their surfaces refreshed with each pass. 3I Atlas had been in the cold void for millions of years, its skin baked by cosmic rays, its ices buried deep. Another difference lies in its orbit. Comets in the solar system follow long ellipses, returning after decades or millennia. 3I Atlas on its hyperbolic path will never come back. This is a once-only encounter. That's what sets it apart most sharply, not how it looks, but how it moves. Comparisons with the other two interstellar visitors highlight the point. Oumuamua was baffling. elongated, tumbling with no gas or dust. Borisov, by contrast, was a classic comet, bright and active. 3I Atlas lands between them, clearly cometary but reserved, not a puzzle like Oumuamua, not a spectacle like Borisov, but something quieter, something steady. To make it more tangible, think of people. Some visitors arrive at a party loudly, drawing every eye. Others slip in mysteriously, leaving you wondering who they were. And then there are those who join calmly, blending in, reminding you of old friends. 3I Atlas is that last type, familiar in every way, but made remarkable by the fact that it came from somewhere else entirely. That's the paradox of 3I Atlas. By every measure, size, chemistry, density, it could be one of our own. And yet it isn't. It belongs to another star, another system, another history. In being ordinary, it becomes extraordinary. Proof that the processes shaping comets here are repeated across the galaxy. So the comparisons leave us with a quiet conclusion. 3I Atlas is both like and unlike our comets. It looks the same, behaves almost the same, and yet its path tells us it is different. In that tension lies its importance. A reminder that the galaxy is full of familiar things, waiting to appear in unfamiliar skies. When astronomers first calculated the path of 3I Atlas, one number stood out above all the others: its eccentricity. Eccentricity is a way of describing the shape of an orbit. If the value is exactly 0, the path is a perfect circle. Between 0 and 1, you get ellipses, stretched ovals, like the paths of Earth, Jupiter, and most comets we know. An eccentricity of 1 means the object follows a parabola, barely bound to the sun, destined to return only after unimaginable stretches of time. But anything greater than 1 means something very different. The orbit is open, hyperbolic, and the object is not bound at all. For 3I Atlas, the eccentricity was calculated at about 1.16. That may not sound like a dramatic number, but in celestial mechanics it speaks volumes. Even slightly above 1, the orbit cannot loop back. Instead, it traces a single curve around the sun, and then heads outward, never to return. That is the unmistakable signature of an interstellar traveler. To picture it more simply, think of runners on a track. Most jog in the smooth loops, circling again and again. That's how asteroids and comets behave, moving on closed ellipses around the sun. But every once in a while, someone cuts across the infield, running in and then straight out the other side. That's what 3I Atlas is doing. Its path cuts through our solar system once, and then it leaves, forever. The orientation of its orbit adds to the story. It approached from a direction tilted compared to the plane where most planets circle. That's another clue. Objects that formed with the planets tend to share the same flat, disc-like orientation. 3I Atlas came in on its own angle. An outsider moving through the familiar crowd of planets with no regard for their alignment. The shape of the orbit also explains why astronomers were so quick to recognize its interstellar nature. With Oumuamua in 2017, it took a little longer because its hyperbolic orbit, an open one-way path past the sun, was calculated after the fact, once enough positions were gathered. With 3I Atlas, the data was clearer almost immediately. Within a day of discovery, its eccentricity was firmly above 1, leaving no doubt. The speed fits the picture. To be on a hyperbolic trajectory, an object must have enough energy to escape the sun's pull. Its path bent slightly as it passed the sun, but never enough to trap it. Instead, gravity simply redirected it, like a stone skimming past a planet, giving it a curve but not a capture. One of the elegant parts of celestial mechanics is how predictable these things are. Once the orbit is measured, astronomers can project the path forward for centuries, even millennia. For 3I Atlas, the future is simple. It will recede into the dark, fading steadily until it disappears from our instruments. Its curve through our solar system is just one brief line in a journey that began light years away. So when scientists say hyperbolic orbit, they're not using jargon for its own sake. They're describing a shape that is fundamentally different from the orbits of the planets and comets we know. That shape is the mathematical proof that 3I Atlas is not from here, that it was born around another star, long ago and now by chance passed close enough for us to notice. Once astronomers confirmed that 3I Atlas was interstellar, the natural question followed: where did it come from? If its orbit shows it arrived from outside the solar system, could we trace that curve backward to a specific star, a system where it might have been born? In principle, that's possible. When you know the speed and direction of an incoming object, you can project its path back across space, seeing where it might have been thousands or millions of years ago. With Oumuamua in 2017, scientists tried just that, searching star catalogs for any candidate systems. For 3I Atlas, the attempt was made again, but here's the difficulty. Space is not still. Stars themselves are in constant motion, orbiting the center of the Milky Way, drifting relative to each other like boats on a slow-moving tide. The further back you project, the more uncertain the calculations become. A tiny error in speed now becomes a vast difference over millions of years. And in the case of 3I Atlas, that's exactly what we face. Current estimates suggest that 3I Atlas entered the solar system from the direction of the constellation Serpens, near the border with Ophiuchus. That points to a region of the sky, but not a particular star. To say it came from Serpens is more about geometry than ancestry. We know where it appeared from our point of view, but not which system gave it its push. What we can say is that objects like 3I Atlas are most likely expelled during the early formation of planetary systems. When giant planets form, their gravity can act like slingshots, flinging smaller icy bodies outward at high speeds. Some are captured in distant orbits, like our Oort cloud. Others are thrown so hard they escape the star's gravity entirely, cast loose into interstellar space. Over billions of years, a galaxy fills with these wanderers, dark, icy fragments drifting between the stars. So 3I Atlas probably began as an ordinary comet in another star system, orbiting quietly until a chance encounter with a massive planet ejected it. That event could have happened tens or hundreds of millions of years ago. Since then, it has been adrift, frozen and silent, until by chance its path carried it near our sun in 2025. And this is the humbling part. Even with the best telescopes and the best models, we will likely never know the exact star of origin. The galaxy is too crowded, the timescales too long, the uncertainties too wide. We can only trace the general direction, not the birthplace. It is as if a stranger walked into a room from the street. You can tell which door they entered, but not which city they traveled from. Still, there's meaning in that mystery. To know that this comet formed around another sun, somewhere in the billions of stars that make up the Milky Way, is already extraordinary. It reminds us that comets are not unique to our solar system. They are universal, shaped by gravity and chemistry wherever planets and stars are born. So when we ask, where did 3i Atlas come from? The truest answer may be simple. It came from the galaxy itself, from the shared processes that build worlds and scatter fragments, from the same physics that shaped our own comets. Its home star may remain nameless, but its presence tells us that we are not alone in having icy wanderers. It's a galactic story, not just a local one. Every comet has a story of arrival and departure. And for 3i Atlas, the departure is just as important as its entrance. Once it curved around the Sun in mid-2025, its path was already set. Outward, away from our star, into the quiet dark of interstellar space again. Astronomers tracked its outbound trajectory carefully. Having passed closest to the Sun, its perihelion, closest point to the Sun, in early August 2025, the comet began to climb outward, moving away at tens of kilometers per second. Even as the Sun's gravity pulled on it, the speed was too great for capture. The curve bent, but it never closed. From Earth, this meant that the window of visibility was limited. Observers estimated that 3i Atlas would remain within reach of large telescopes for only a few more months. By the end of 2025, it would have faded past the sensitivity of most instruments. Smaller amateur telescopes would lose it even sooner, as its faint coma and tail diminished against the background stars. In purely orbital terms, the comet is now outbound on a hyperbolic escape path, moving towards the constellation Scutum. But that doesn't mean it has a destination in the sense we usually imagine. Interstellar space is vast, and the chances of it passing close to another star anytime soon are vanishingly small. For all practical purposes, it is headed into emptiness. Still, we can estimate the scale of its journey. At its current speed, about 61 kilometers per second, 3i Atlas covers more than 5 million kilometers every day. In a year, that's nearly 2 billion kilometers, farther than the distance from the Sun to Saturn. In 10 years, it will be well past the outer edges of the solar system. In 1,000 years, it will be a faint ghost drifting among the nearby stars. And in 1,000,000 years, it will have crossed hundreds of light years, indistinguishable from the countless other fragments wandering the galaxy. What's striking is how brief its visit feels to us. For billions of years, it traveled unseen, and for just a few months in 2025, it became visible, faintly, quietly, to human eyes. Then, just as quickly, it will be gone again. The timescales are almost absurd. A cosmic lifetime spent in darkness, punctuated by a blink of light as it passed our star. This transience is why astronomers move so quickly after its discovery. Every day mattered. Each observation taken in July and August added to the knowledge that would be all we'd ever gather from this comet. Once it slips away, there will be no second chance. So where is 3i Atlas going? The honest answer is back to the galaxy, outward away into the endless night. Its orbit shows no return, no loop back into view. For us, its story has a beginning and an end, but for the comet, it is simply continuing, a journey without pause, without destination, across the deep. When we picture 3i Atlas moving through the solar system, it's easy to imagine it slipping by untouched, as if gliding on a straight line. But gravity is everywhere, and every massive body, sun, planets, even large moons, tugs on anything that passes. The story of 3i Atlas's trajectory is partly the story of how those pulls shaped, or barely shaped, its flight. The dominant influence, of course, was the Sun. As the comet approached, The sun's gravity bent its path into a sharp curve. Without that pull, it would have passed in a straighter line, only slightly deflected. Instead, the sun acted like a pivot point, swinging it around in a wide arc. Even so, the speed was too great for capture. Rather than falling into orbit, it simply slingshotted, leaving on a new heading, outbound forever. What about the planets? Naturally, astronomers checked whether giants like Jupiter or Saturn came anywhere close to its path. Jupiter especially has been called the solar system's gatekeeper because its immense gravity often redirects comets or even ejects them. But in this case, 3I Atlas passed at a safe distance. Its trajectory was not significantly altered by any planet. That's part of why the orbit could be pinned down so precisely. No major perturbations, just the clean bend of the sun's gravity. Still, even small influences matter. As the comet passed through the inner system, tiny gravitational nudges from Earth, Venus, and other planets were included in the models. They didn't change the outcome. An escape path was always certain, but they adjusted the fine details of its track. The precision of modern orbit calculations is astonishing. With dozens of observations, astronomers can measure positions to fractions of an arc second, enough to detect those subtle tugs. It's worth noting how stable this made the prediction. For many comets, uncertainties linger until months of data are collected. For 3I Atlas, the hyperbolic nature of the orbit was clear almost immediately. And with no close planetary encounters to complicate things, the trajectory remained solid. By mid-July, astronomers could already say with confidence, this comet is leaving, and nothing in the solar system will stop it. In a way, that stability feels fitting. An interstellar traveler like this carries the imprint of forces far older than our sun. Ejections from giant planets in another star system, nudges from ancient neighbors, the long drift of galactic tides. By the time it reached us, its momentum was so great that even Jupiter, the giant that rules our local comets, had no chance to capture it. So the gravitational story of 3I Atlas is simple but profound, bent by the sun, untouched by the planets, and steady in its escape. Our system tugged at it, curved it, illuminated it for a short while, and then let it go. The comet arrived with its path already written, and all we could do was watch it play out. When you think about comets, you might imagine something that lingers in the sky for weeks or months, perhaps even returning after many years. But interstellar comets, like 3I Atlas, live on very different timescales. For us, their visits are fleeting, barely more than a passing glimpse against the backdrop of cosmic time. 3I Atlas was first spotted on July 1st, 2025. At that point, it was already inbound, tens of millions of kilometers from the sun, and its brightness was modest, just enough for the automated Atlas survey to catch it. Within days, professional observatories and amateurs alike confirmed it, and the race began to gather as much data as possible before it was gone. Its closest approach to the sun, perihelion, came in early August 2025. That was the moment when the comet was brightest and most active, shedding gases as its surface warmed. Even then, it never became visible to the naked eye. Only with telescopes could its faint glow be traced. But for astronomers, this was the peak opportunity. The days and weeks around perihelion were the most valuable window of all. After perihelion, the comet began its outward climb. By September, it was already dimming. Large observatories could still track it, but smaller telescopes struggled. Projections showed that by the end of 2025, 3I Atlas would be too faint even for professional instruments, effectively slipping back into invisibility. A discovery in July, a perihelion in August, and by December, gone. That's just half a year of observational life. Compare that to many solar system comets, which can be studied for years before and after perihelion, and you see how brief this chance really was. For Oumuamua, the window had been even shorter, just a couple of weeks before it faded too much. Borisov gave a few months of brighter activity. 3I Atlas sat between them. Longer than Oumuamua, shorter than most periodic comets, but still fleeting. On the scale of its whole journey, those months are almost laughably small. This is an object that has traveled for millions of years, perhaps billions, across interstellar space. And yet, the part of its story that intersects with humanity is measured in weeks. Imagine a long train passing by, and all we see is a single car in the middle, here for a moment, then gone into the night. For scientists, this is why every observation mattered. Each night's spectrum, each image, each brightness measurement, added to the only record we will ever have. Once 3I Atlas fades, it will never be recovered. No second approach, no return visit. The data we gathered in 2025 is the sum total of what we'll ever know. For us listening now, it's a reminder of scale. Human time, days, months, years, means little to an interstellar traveler. Its clock runs in millions of years. Its journey spans light years. To us, it was a seasonal guest in the summer of 2025. To the galaxy, it is simply continuing a voyage without end. So the timescale of 3I Atlas's passage is both humbling and beautiful. Brief enough that we had to act quickly, long enough that we could gather real science, and vanishingly small compared to the lifetime of the comet itself. It arrived, it lingered just long enough to be noticed, and now it is gone again, back into the immeasurable dark. With the discovery, the measurements, and the orbit all secured, the bigger question comes into focus. Why does 3I Atlas matter? Why should astronomers spend so much energy studying a faint, forgettable-looking comet that will be gone in a few months? The answer is simple but profound, because it carries a story from somewhere else. Until 2017, we had never directly observed an interstellar object. Everything we knew about comets came from our own solar system, our Kuiper belt, our Oort cloud. We could guess that other stars must produce comets too, but guesses are not evidence. Then came Oumuamua, Borisov, and now 3I Atlas. Each one is a piece of direct proof. Other star systems form icy bodies, and some of those bodies get ejected, cast into the galaxy to wander forever. That matters because it confirms something fundamental about how planets and stars form. In our own system, giant planets like Jupiter and Saturn likely played a role in shaping the Oort cloud, flinging countless comets outward to its farthest reaches. If 3I Atlas formed around another star, the same process must have happened there. Its very existence tells us that planet formation is not unique. Across the Milky Way, whenever stars grow and planets assemble, comets are born as a byproduct. It also matters because these visitors are samples, natural probes delivered across interstellar space. We may never send spacecraft to other stars, at least not in our lifetimes, but objects like 3I Atlas bring material from those systems directly to us. Even faint gases escaping from its surface carry chemical fingerprints of its origin. By studying them, we glimpse the chemistry of another sun's nursery, billions of years and light years removed from our own. There's also something humbling about the scale. Our telescopes are powerful, but they cannot yet resolve exoplanet surfaces or scoop material from another system. Interstellar comets are one of the only ways we can hold something truly foreign in our instruments. Material forged elsewhere, drifting into our reach for just a moment. And while 3I Atlas looks ordinary, that too is significant. Its small size, shadowed surface, and familiar composition suggest that comets everywhere may share common recipes. The physics of ice and dust, the chemistry of carbon and water, seem to play out the same way across the galaxy. Ordinary here, ordinary there. And in that ordinariness lies the extraordinary truth that we are not unique. So when astronomers gather every bit of data they can on 3I Atlas, they aren't just cataloging another comet. They're seizing one of the rare chances to study a messenger from another star system. Each spectrum, each brightness curve, each faint image is a glimpse into how planets and comets form elsewhere. For a science that usually relies on inference and distant starlight, that's an opportunity too rare to waste. In short, 3I Atlas matters because it confirms a pattern, delivers a sample, and expands our perspective. It is proof that our solar system is not an exception, but part of a wider story. The galaxy itself full of icy wanderers, carrying their stars' histories through the dark. When Atlas was confirmed as an interstellar object, astronomers naturally placed it alongside the only two others we've seen, Oumuamua, 2017, and 2I Borisov, 2019. Together, they form a tiny catalog, just 3 entries so far. But even with only 3, the comparisons are revealing. Oumuamua was the first, and it was strange. It had no coma, no tail, nothing to mark it as a comet. It was just a bare, elongated body tumbling as it passed. Some estimates suggested it was shaped like a cigar, others like a thin pancake. Its brightness shifted wildly as it spun, hinting at a highly irregular form. Most puzzling, it accelerated slightly as it moved away from the sun. An effect usually caused by gas jets, but none were seen. To this day, Oumuamua remains mysterious, sparking theories from icy shard to exotic fragment. 2 years later came Borisov, and it was much more familiar. Discovered by amateur astronomer Gennady Borisov in Ukraine, it showed all the hallmarks of a comet. A bright coma, a long dust tail, clear signs of activity. In many ways, it was unremarkable. If it hadn't been interstellar, it could have been mistaken for any solar system comet. But that ordinariness was its gift. It proved that interstellar objects don't have to be exotic. They can look just like the ones we know. And then came 3I Atlas in 2025. In character, it sits somewhere between the first two. Unlike Oumuamua, it clearly showed cometary activity, a coma, a tail, gases detected in spectra. But unlike Borisov, it was faint, subtle, with activity that never reached dramatic levels. It's as if the first object was too strange, the second too familiar, and the third balanced in the middle. Recognizably a comet, but with a quieter personality. This comparison matters scientifically. With only 1 or 2 examples, it was impossible to know whether interstellar objects were oddities or common types. Oumuamua suggested something unusual. Borisov suggested something ordinary. 3I Atlas shows us a middle case that hints at diversity. Just as our solar system has comets that are bright, faint, active, or quiet, other star systems likely produce a wide range of bodies too. It also helps refine expectations for the future. When the next interstellar object is spotted, And it will be, thanks to ever-improving surveys. Astronomers won't be surprised whether it looks exotic, ordinary, or something in between. 3i Atlas proves the spectrum is wide. On a more human level, the trio forms a story. Oumuamua was the mystery guest who left too soon. Borisov was the familiar neighbor, easy to recognize. And 3i Atlas is the quieter visitor, present long enough to be studied, cometary but not flamboyant, steady rather than spectacular. Each has its own role, and together they show us that interstellar wanderers are varied, not one note. So in the grand narrative, 3i Atlas is important, not because it shocked us, but because it didn't. It filled in the middle ground. It told us that some interstellar comets can be modest, unassuming, even easy to overlook, yet still carry the profound weight of another star system in their dust. One of the most intriguing parts of studying 3i Atlas was its chemistry. Even though it appeared faint and quiet compared to brighter comets, the gases escaping from its surface carried fingerprints, subtle signals written in light. Spectrographs on ground-based telescopes split its glow into patterns of color, and within those patterns were familiar signatures. Scientists detected emissions from molecules like CN, cyanogen, and C2, diatomic carbon, the same compounds that show up in many solar system comets. These molecules aren't exotic. They're ordinary, found again and again whenever frozen carbon-rich material warms near a star. Yet their presence in 3i Atlas carried weight. They told us that the chemistry of comets may be universal. Why is that important? Because it suggests that when stars form and planets begin to grow, the leftover ingredients assemble into the same kinds of icy fragments everywhere. Water, carbon compounds, silicates. These seem to be the basic recipe not just here, but across the galaxy. In other words, comets may be a natural outcome of star and planet formation, no matter the system. That has implications for life, too. Comets in our solar system are thought to have delivered water and organic molecules to early Earth, seeding the conditions for biology. If comets like 3i Atlas form with the same ingredients elsewhere, then the building blocks of life are not unique to us. They could be scattered widely, frozen into billions of small bodies orbiting billions of stars, waiting to be delivered to planets, just as they may have been here. At the same time, 3i Atlas was not a chemical twin to Borisov. Borisov showed stronger emissions of certain gases, like cyanogen, and had a brighter coma overall. 3i Atlas's signatures were fainter, perhaps because its surface was more hardened by cosmic radiation during its long drift through interstellar space. That difference adds to the growing picture of diversity. The recipes may be the same, but the exact flavors vary. Another subtlety was the dust. The tail of 3i Atlas contained fine grains, scattered by sunlight, giving it a bluish hue in some images. Dust is a powerful clue because its size and distribution depend on the strength of activity and the nature of the nucleus. In this case, the dust suggested gentle release. Nothing violent, just steady exhalation. Again, ordinary for a comet, but extraordinary for one that formed around another star. So what does this chemistry tell us? That 3i Atlas is both familiar and foreign. Familiar because the molecules are the same ones we know. Foreign because they condensed under a different sun, perhaps billions of years ago, in a star system we will never visit. To hold spectra of its gas is to hold a message from another world, not a message written in words, but in molecules. And that, ultimately, is why 3i Atlas matters. Its chemistry whispers that the galaxy is consistent. Stars form, planets grow, and comets condense. The building blocks repeat from one system to the next. In studying its faint glow, we are reminded that our solar system is not a special case, but part of a greater pattern that extends across the stars. Every comet tells a story of origin, and for 3I Atlas, that story likely begins not in deep space, but in the early days of another planetary system. To understand why, you need to imagine how stars and planets are born. A young star forms from a collapsing cloud of gas and dust. Around it, a protoplanetary disk spins, flat, wide, filled with material. In that disk, small particles stick together, forming planetesimals and eventually planets. But the process is not gentle. Gravity pulls, orbits cross, and giant planets, when they appear, act like wrecking balls. They scatter smaller bodies outward, some inward toward the star, others into distant reservoirs, like our Oort cloud. And some are launched so fast, they escape the star's grip entirely. That's almost certainly how 3I Atlas began. Once, it was just one of many icy fragments orbiting a distant sun. But at some point, perhaps hundreds of millions of years ago, a massive planet crossed paths with it. Jupiter-sized worlds are especially efficient at this. Their strong gravity can fling smaller bodies into wild new paths, turning quiet orbits into escape routes. For 3I Atlas, one such encounter likely gave it the push it needed to break free, sending it into the galaxy as an eternal wanderer. This idea isn't just speculation. It's consistent with what we see in our own system. Models suggest that most comets ever formed here didn't stay. When Jupiter and Saturn took shape, their gravity flung countless icy planetesimals outward. Some were caught in long orbits far from the sun, forming the Oort cloud. But many more were ejected completely, set adrift into interstellar space. If that happened here, it surely happened around other stars too. 3I Atlas is one of those countless castaways. What makes this fascinating is the implication: interstellar space is probably full of such bodies. For every Oort cloud that clings to its icy stockpile, there are likely billions of comets expelled into the galaxy, drifting unseen until they pass close enough to a star like ours to be noticed. 3I Atlas is just one of them, caught in our telescopes by chance. In this sense, the comet is not just a curiosity, it's a sample of a process we can't otherwise watch. We cannot peer directly into most protoplanetary disks to see comets being flung out. But when an interstellar object appears, it is evidence that this scattering really happens. It confirms the models, shows us the aftermath. There's also something poetic in thinking about it this way. Our solar system likely ejected trillions of icy fragments in its youth. Some of them may still be drifting today, perhaps already passing through other star systems, unseen by the beings who might live there. Meanwhile, their fragments drift our way. 3I Atlas may be one of those echoes of another system's chaos, a small, fragile survivor of a time when planets were still finding their places. So when we look at 3I Atlas, we're not just studying a lone comet. We're glimpsing the messy birth of a star system long ago. Its path through our skies is proof that the process of making planets is universal, and that it leaves behind wanderers, travelers, who carry the scars of their ejection across the galaxy. When scientists talk about comets, they often bring up not just astronomy, but life itself. That may sound dramatic, but the link is real. Comets are carriers of water and organic molecules, the raw ingredients that on a young planet can set the stage for biology. On Earth, many researchers believe comets played a crucial role in our history. In the early days of the solar system, constant impacts delivered vast amounts of water and carbon compounds to the surface. Those impacts may have filled the oceans and seeded the chemistry that would later lead to life. While the exact proportions are debated, the idea is simple. Comets are not just icy debris, they are couriers of habitability. Now take that idea and extend it beyond our solar system. 3I Atlas showed us that comets with familiar chemistry form around other stars too. Its faint glow carried signatures of carbon-based molecules that are also present in our comets. That means the building blocks of life, water ice, organics, dust, are not unique to us. They're common enough to ride between stars. That realization connects to a concept called panspermia, the idea that life, or at least its chemical seeds, could be spread by comets and asteroids across cosmic distances. Most scientists are cautious with that word. It doesn't mean bacteria are hitchhiking across light years, but it does mean the molecules essential for life can be delivered widely. If Earth was seeded this way, then worlds around other stars may be too. Interstellar objects like 3I Atlas are proof of the mechanism. They show that icy fragments really do leave their birth systems and drift across the galaxy. Most will never strike a planet, but some might. And even a small chance becomes significant when multiplied by billions of years and billions of stars. Over time, the galaxy becomes a place where water and organics are scattered like dust, increasing the odds that somewhere conditions will be right for life to take hold. There's another angle too. By studying the chemistry of 3I Atlas, astronomers can compare it to comets in our own system. If the recipes are similar, it suggests that the universe is full of worlds starting with the same ingredients. That doesn't prove life is common, but it strengthens the case. Life on Earth may not be a miracle of rarity, but a natural outcome when the right pieces fall together. For people listening at night, drifting towards sleep, think of it like this. Every comet is a tiny package of chemistry, sealed and frozen, carried through space. Some are local, circling the sun. Some are foreign, like 3I Atlas, cast off by another star. Each carries water, carbon, dust. And together, across the galaxy, they sprinkle the ingredients of life into places we will never see. So the significance of 3I Atlas for the search for life is quiet, but powerful. It doesn't prove anything directly. It doesn't answer the question of whether we're alone. But it whispers that the universe is stocked with the same raw materials everywhere. And if life could begin here, perhaps it could begin elsewhere, too. When Oumuamua appeared in 2017, astronomers were caught off guard. By the time they realized what it was already faint, heading out of reach. With Borisov in 2019, they had a little more time, but still only months. By the time 3I Atlas arrived in 2025, the community was better prepared. Wide field surveys were watching, and telescopes turned quickly. Even so, the window was short. If we want to truly understand interstellar visitors, we'll need to be ready before the next one comes. That's where new instruments enter the story. The Vera C. Rubin Observatory in Chile, set to begin full operations in the mid-2020s, will revolutionize the way we search the sky. Its Legacy Survey of Space and Time, LSST, is designed to scan the entire visible sky every few nights, capturing billions of stars, galaxies, asteroids, and comets. With that kind of coverage, the chance of missing an interstellar visitor will shrink dramatically. Instead of stumbling upon them, we may begin to expect them. Astronomers predict that once Rubin is fully online, discoveries of interstellar objects could rise from once a decade to once a year, or even more often. That's an extraordinary leap. In a single human lifetime, we might gather dozens of examples instead of just a handful. With more data points, the science deepens. We could begin to categorize interstellar objects, build statistics, and see patterns emerge. How many look like Oumuamua? How many like Borisov? How many like 3I Atlas? And how many surprise us entirely? Other facilities will help too. Space telescopes like James Webb can capture faint spectra, revealing chemical details even from distant or dim comets. Planned missions to study near-Earth objects may be retargeted if an interstellar body comes close enough. And some researchers even dream of something bolder, a spacecraft ready to launch on short notice, capable of intercepting one of these visitors for a close-up look. The European Space Agency has already considered such a mission concept, called Comet Interceptor. The idea is to build a spacecraft, keep it waiting in space, and then send it to meet a newly discovered comet, ideally an interstellar one. If such a mission succeeds, it would give us our first direct samples of material from another star system. For now, though, the next steps are about patience and preparation. Every new survey telescope, every new data pipeline, increases the odds that when 4I arrives, the fourth confirmed interstellar object, we'll be ready. Maybe it will be another faint, quiet comet. Maybe it will be something strange, like Oumuamua. Or maybe it will be brighter, closer, and more generous with data than any we've seen before. Think about how quickly the story has grown. From 0 interstellar objects before 2017 to 3 by 2025. In just 8 years, our understanding has expanded from theory to direct evidence. Imagine what the next decades will bring as technology sharpens and surveys sweep the skies night after night. So 3I Atlas is not just significant for what it is, it's also part of what comes next. Each visitor teaches us, but also prepares us for the next. The galaxy is full of wanderers. The question is no longer whether they exist, but how many we will find, and how much we can learn from them. Sometimes the numbers and data can feel abstract. Eccentricities, velocities, magnitudes. But step back, and the meaning of 3I Atlas becomes something much more human. It's not just a comet. It's a reminder of how connected we are to the wider galaxy. For centuries, people looked at the night sky and wondered whether other worlds existed. Telescopes confirmed planets orbiting other stars, but they remain far away, unreachable to us. Interstellar comets are different. They are pieces of those other systems, arriving on their own, crossing the gulf between stars and drifting briefly into our sight. In them, the question of "are we alone?" turns from distant speculation into something tangible. Here, for a moment, is material forged elsewhere, brushing past us. Oumuamua gave us wonder through mystery, its strange shape, its unexplained acceleration. Borisov gave us comfort through familiarity, a comet like any other, only foreign in origin. 3I Atlas gave us perspective. It reminded us that the galaxy does not just contain the exotic and the ordinary, but everything in between. Diversity is the rule, not the exception. This diversity deepens our sense of belonging. When we see that the chemistry of 3I Atlas resembles our own comets, we realize that the laws of physics and chemistry don't stop at our sun's edge. water, carbon, dust. These are not ours. They are galactic, shared across billions of systems. Our solar system is just one small variation on a theme that plays everywhere. There's also humility in how fleeting the encounter was. For millions of years, 3I Atlas traveled unseen. For just a few months, it crossed our skies, faint and modest, then slipped away again. In that brief overlap, humanity noticed. Telescopes pointed, data flowed, and for the rest of time, we will carry the record of its passage. That moment of noticing is what makes us participants in the galaxy, not just bystanders. Even for those who never looked through a telescope, the knowledge matters. Somewhere out there, fragments of other stars wander in silence, and sometimes they pass us by. Each one is a message. You are part of something bigger, a galaxy full of worlds and processes, repeating again and again. So the significance of 3I Atlas is not just scientific, it's existential. It shows us that the boundaries of our solar system are not the boundaries of our story. The galaxy is dynamic, filled with movement and exchange. Material crosses between stars. Systems are not sealed but porous, connected by wanderers like this comet. And perhaps that is the deepest meaning of all. 3I Atlas is not just a visitor. It is a thread in the fabric of the Milky Way. And by watching it, we catch a glimpse of how tightly woven that fabric really is. Numbers alone rarely stick in our minds. To feel the reality of 3I Atlas, it helps to place its facts alongside things we know. Let's start with its speed, because that's one of its most defining traits. That's 220,000 kilometers every hour, enough to travel from Earth to the Moon in just over an hour. To compare, a commercial jetliner cruises at about 900 kilometers per hour. That means the comet is moving more than 240 times faster than the planes we fly in. Even the International Space Station, orbiting Earth at 7.7 kilometers per second, would look sluggish. 3I Atlas moves nearly 8 times faster. Picture Earth's circumference, 40,000 kilometers around. At its current speed, 3I Atlas could loop the entire planet in a little over 10 minutes. Imagine standing still and knowing that somewhere in the sky, an object from another star system could circle your world 6 times before you finish a cup of tea. Distance offers another perspective. The comet's nucleus is only a few kilometers wide, but its tail stretched thousands of kilometers. To compare, that's like an object the size of a small city trailing a veil longer than the distance between New York and Los Angeles. From our vantage point, the tail looked faint, barely visible, but in sheer scale it was immense. And then there's the journey itself. Interstellar space is vast beyond comprehension. The nearest star system, Alpha Centauri, is over 40 trillion kilometers away. At 61 kilometers per second, 3I Atlas would need more than 20,000 years just to cover that gap. Even at its astonishing pace, the stars are unimaginably far. So speed and distance combine into something almost paradoxical. To us, the comet seemed to rush past, its entire visit compressed into a few months. Yet in galactic terms, it drifts slowly, barely scratching the surface of the space between stars. What feels fast here is leisurely out there. These comparisons matter because they make the comet real. Instead of abstract numbers, you can hold images. Earth circled in minutes. A veil of dust stretching like a continent, a journey so long it would outlast civilizations. That's what 3I Atlas embodies. Both immediacy and eternity, the quickness of a passing moment, and the slowness of a galactic crossing. If speed defines 3I Atlas's journey, Size helps us picture the traveler itself. Astronomers estimate the nucleus to be only a few kilometers across, likely between 3 and 5 kilometers in diameter. That's small in cosmic terms, but in human terms, it's enormous. The entire island could fit within the nucleus of 3I Atlas. Or think of Mount Fuji in Japan, rising more than 3 kilometers above sea level. The comet is comparable in scale, not as majestic perhaps, but similar in raw size. And yet, compared to planets, it's nothing. Earth's diameter is 12,700 kilometers. Even the smallest round moons in our solar system measure dozens of kilometers across. 3I Atlas is just a pebble next to those worlds. That's part of why it cannot hold a proper atmosphere or maintain strong gravity. On its surface, you could leap into space with a strong jump. But size isn't only about the nucleus. The coma, the cloud of gas and dust that surrounded it, stretched tens of thousands of kilometers across. That's larger than Earth itself. Imagine a rocky core, the size of a city wrapped in a mist wider than a planet. That's what telescopes saw. A faint, ghostly sphere of gas surrounding a tiny, hidden heart. The tail added another layer of scale. Even though it was faint, Hubble measured it extending hundreds of thousands of kilometers. For comparison, that's more than the distance from Earth to the Moon. To our eyes, the tail was subtle, barely more than a haze. But in reality, it was a structure vast enough to cross from one world to another. These juxtapositions help resolve the paradox. Comets are small and large at once. The nucleus itself could be walked across in an afternoon, but the halo of gas around it could engulf entire planets. They are fragile in mass yet immense in presence. 3I Atlas fits this pattern well. It was no giant, no rare, great comet blazing overhead. But its modest nucleus, wrapped in an atmosphere larger than Earth, drifting with a tail longer than the Earth-Moon gap, was still a spectacle, just one, revealed only through careful instruments. For the listener, it's worth pausing on the image. A lump of dark ice the size of a city, trailing a veil longer than the trip to the Moon, drifting silently across the sky. Small enough to be forgotten in galactic terms, yet large enough to hold centuries of human imagination. Facts and numbers help. But sometimes the best way to understand an object is to imagine yourself there. So let's take a quiet thought experiment. What would it be like to stand on the surface of 3I Atlas? First, the gravity. With a nucleus only a few kilometers wide and density far below rock, its pull would be almost imperceptible. On Earth, you weigh your full normal weight. On the Moon, you'd weigh about a sixth of that. On 3I Atlas, you'd weigh almost nothing. So little that a single jump could launch you into space. Walking would feel impossible. Every step would send you floating upward. To stay grounded, you'd need anchors, spikes, or cables. The landscape would look nothing like Earth. Instead of smooth plains or seas, you'd see jagged cliffs of dark ice, slopes of loose dust, and pits formed where gas once vented into space. The surface would be pitch black, blacker than asphalt, reflecting only a few % of the sunlight. To your eyes, it would feel less like snow and more like walking across burnt coal-like surface. The sky would be extraordinary. With so little gravity, the horizon would curve tightly beneath you. Look straight ahead, and you might see the edge of the comet, falling away after just a couple of kilometers. Above, the sun would shine fiercely, but without the scattering effect of an atmosphere, the rest of the sky would remain jet black, studded with stars. The contrast would be stark. brilliant sunlight, sharp shadows, and a background of infinite night. Near perihelion, you might even witness the comet's activity firsthand. Jets of gas could erupt from cracks, spraying fine dust outward in silent plumes. On Earth, such power would roar. Here, in vacuum, it would be soundless, only visible as shimmering streams against the black sky. If you stood nearby, grains of dust might lift gently into space, carried away by sunlight itself. Despite the activity, the environment would be deathly cold. Even near the sun, the surface would remain well below freezing. Dig just a few centimeters, and the temperature would drop to levels colder than any polar night on Earth. Without protection, you'd freeze instantly. With protection, you'd feel the eerie quiet. No wind, no air, only the crunch of boots against fragile dust. And then there's the scale. You could cross the entire comet in an afternoon hike, just a few kilometers from one horizon to the other. But as you walked, you'd know that this small body carried with it billions of years of history, fragments of a world you'll never see. Beneath your feet lies ice formed around another star, chemistry older than your planet, preserved in darkness until now. It's an impossible journey, of course. No spacecraft will land on 3I Atlas. But in imagining it, we bridge the gap between data and experience. We turn eccentricities and magnitudes into feelings. The looseness of gravity, the blackness of the surface, the sharp contrast of sun and stars. And in that mental picture, the comet becomes not just an object in the sky, but a place that passed through our solar system once quietly before continuing on its way. Astronomy often leans on metaphors because raw numbers alone don't capture the feeling. Atlas, more than most, invites that softer language. It's not just a comet. It's a traveler, a messenger, a ripple in the fabric of the galaxy. Think of it first as a traveler. For millions of years, it drifted in silence, carrying momentum from a star system we'll never know. No engine pushed it, no crew guided it. It simply followed the rules of gravity and inertia, moving in a straight line until our sun bent its path. Its journey reminds us that movement is the natural state of the universe. Everything drifts. Everything wanders, even fragments of ice and dust. It can also be seen as a messenger. The molecules released from its surface, water, carbon compounds, fine dust, are pieces of another world, carried across light years to reach us. We cannot travel to its home, but in a sense, its home traveled to us. Even a faint spectrum captured by a telescope is a message. You are not alone in having comets. The galaxy is full of them. Or picture it as a ripple. In the pond of the Milky Way, stars and planets are stones dropped into water. Each one sends out ripples, gravitational influences, scattered fragments, ejected comets. 3I Atlas is one such ripple, crossing our pond briefly before moving on. We noticed it because our instruments are now sharp enough to catch faint disturbances, but countless others must have passed unseen before. These images don't replace the science, they complement it. But the feeling of a city-sized lump of ice traveling from another sun, glowing faintly as it passes, is something numbers alone cannot give. For those listening at night, drifting towards sleep, that's perhaps the most important part. 3I Atlas is not a monster or a threat, not a spectacle blazing overhead. It's something quieter, gentler, a reminder that the galaxy is alive with motion, and that sometimes, by chance, a visitor appears to remind us we are part of that larger whole. So if you think of 3I Atlas at all after this, picture it not as a statistic, but as a companion, passing silent, carrying with it the memory of another place. A traveler from afar, a messenger of chemistry, a ripple from the stars. Here for a moment, then gone, leaving us with wonder, and perhaps with dreams that drift as quietly as it does. As we come to the end of this long journey, it helps to pause and gather the pieces of 3i Atlas's story. Over the past months of its brief visit, astronomers collected thousands of data points, and each one told part of the tale. We learned how it was first discovered on July 1st, 2025, by the Atlas survey in Chile, a faint moving point flagged by software and quickly confirmed worldwide. We saw how its orbit, with an eccentricity above 1, marked it as interstellar, a one-way traveler from beyond the sun's reach. We studied its physical traits: a nucleus about 3 to 5 kilometers across, with a burnt, coal-like surface, reflecting only a few % of sunlight. A mass measured in tens of billions of tons, but porous, fragile, lighter than ice in density. Spinning slowly, shaped irregularly, yet stable enough to hold together. Its chemistry told another part of the story. Carbon-bearing molecules, water ice, fine dust, all familiar, all ordinary, yet extraordinary, because they formed under another sun. The gases it released near perihelion were messages from a different world, written in the universal language of molecules. We traced its path, entering from the direction of Serpens, bending around the sun, and leaving toward Scutum. No planet altered its course. No gravity but the sun's could touch it. Its timescale was fleeting. Discovered in July, brightest in August, gone by year's end. A million-year journey reduced to months of visibility. We asked why it matters. Because it confirms that other systems form comets. Because it delivers samples of material we cannot otherwise reach. Because it proves that the chemistry of water and carbon is not confined to our own skies. Because it expands our perspective of what is normal, not local, but galactic. We compared it to its siblings, Oumuamua, the mysterious, Borisov, the familiar, 3i Atlas, the quiet middle ground. Together they reveal variety. Together they whisper that interstellar wanderers are not rare exceptions, but part of the fabric of the Milky Way. And finally, we placed it in human terms, circling Earth in minutes, the size of a city, a tail longer than the Earth-Moon distance. A traveler you could imagine walking across, yet one that will never return. In all these ways, 3i Atlas became more than a point of light. It became a story of discovery, of chemistry, of movement, of connection. Now, as we let the comet fade from view, it's worth reflecting on the nature of encounters like this. For the comet, nothing has changed. It continues its path outward into the dark. It has no awareness of us, no purpose in passing. It is simply following momentum given long ago, long before humans walked the earth. For us, though, the encounter means something. We noticed. We pointed telescopes, gathered spectra, compared data, and in doing so, wove its brief passage into human knowledge. Long after it has vanished, our records will remain. Future generations will be able to look back at 2025 and know, in that year, a fragment from another star drifted through our skies. It is easy to feel small in the face of such vastness. A traveler millions of years old, crossing light years, appearing to us for only months. But there is comfort too, because by recognizing it, by telling its story, we remind ourselves that we are part of this galaxy. We are not outside it, but inside, woven into the same rhythms of gravity and chemistry. So as 3i Atlas recedes, imagine it one last time. A small, dark body, trailing a faint veil of dust, moving silently past the sun. Picture it shrinking in the distance, fading beyond telescopes, continuing on into the deep. Somewhere in the future, perhaps another civilization will notice it, as we did, and wonder where it came from. For us, its chapter is closed, but its journey continues, and in that continuing, we find both humility and wonder. A reminder that the universe is larger than our brief lives, yet generous enough to let us glimpse its travelers now and then. So tonight, as you drift into rest, let 3i Atlas be your companion. A quiet visitor, here and gone, carrying with it the assurance that the galaxy is full of motion, full of connection, full of stories, waiting to be noticed. Sleep well, and let the comet's journey guide you into dreams as endless as the stars. Good night.